quickly recapitulate what you were trying to do yesterday and see if you have any problems about it. See, what we said was that by means of partial response signaling, what we are trying to do is designing. We are trying to design pulse shapes which introduce a certain amount of intersignal interference in a controlled manner, right? In the sense that at the sampling instance, the contribution that one is getting at a particular sample value is not only coming from the bit that is being transmitted in that particular interval, but also we get a finite interference or a contribution from some other transmissions in the previous bits or succeeding bits. In most of the examples we have discussed through introduction of delays, it's mostly previous bits, right? So for example, in the case of duo-binary signaling, the pulse shape was such that at the designated sampling instance, the sample values were contributed by the present bit and the previous bit. That is, xk, the sample value of the waveform at the time instant k t0 plus t0 by 2 is equal to ak plus ak minus 1. Right? This happens because of the specific pulse shape that is being used. That is, at these sampling instance, these two pulse values, these two pulses contribute non-zero values. All other pulses corresponding to all other transmissions on either side of the kth bit interval contribute a zero amplitude at this sampling instant, right? Therefore, the net effect is that in the case of duo-binary signaling, when you sample at the kth instant, when I say kth instant, it means we are talking about t equal to k t naught plus t naught by 2. We get a contribution equal to ak and also same amount of contribution from the previous pulse. I don't have to show you that figure again, which I have showed you a number of times before, alright, which brings out this fact. Similarly, in the case of modified duo-binary, we now using a pulse shape which gives us xk equal to ak minus 2. Yes.
That in this we are assuming the linearity of the channel. Is it
yes.
really expected?
If our model with which we are working is that everything is linear. In fact, if you remember, the channel is being modeled as a linear filter, and what we are talking about as xk here is the output of 3 filters in cascade, right, whose input is an impulse sequence and the output is xt, right. The 3 filters that we are referring to are number 1 at the transmitter, which is some kind of a pulse shaping filter. 2, the channel itself works as a filter with its band limited transfer function, whatever it may be. And 3, you will have a filter at the receiver to make an optimum decision regarding each bit interval, typically a match filter kind of receiver, right. So it is a sum total of all these 3 filters that we are looking at over here, right, cascade of these 3 filters. Yes, it is a linear channel we are assuming. That assumption is correct. Okay. Does this sound all right to all of you now? No. Where is it? Where is the doubt? Okay, I'll have to pull them out of my hat here again. Which waveform you'd like to look at? The modified duo-binary. This is the modified duo-binary waveform. Right? Right. Now, of course, if you remember, the realization with which we are working has a delay of 2t0 seconds. Right? Because what we are saying is
So where is something exactly?
We are sampling at every t0 seconds. So what you have to really say is, if you were to superimpose these waveforms one after another every t0 seconds, right, what will happen? That is a question that you are looking at. Okay, and let me just again pull up something from. Okay. Remember this picture? This is a practical possible method of realizing this wave shape, except for a delay of 2t0 seconds. 2t0 or t0? What was it? 2t0.
Yes, sir, 2T.
2t0. Okay. Okay. That means we are what of course we are going to get here is, I should have written pt here. I'm distinguishing between pt and xt. Xt is the total superimposed waveform after a number of, when you are getting a sequence of impulses, whereas pt is a single pulse. Okay, so this is a single pulse and xt is a superimposition of such pulses corresponding to the specific data sequence that is being transmitted. Alright, so do you remember this equivalence? Generation of this spectrum through this kind of a mechanism, right? What I try to then tell you is that one can generate a modified duo-binary signal scheme, this kind of a pulse shape.
In this case, if AK and AK minus 2 are the same, then it is okay, understandable.
No, it is an arbitrary random sequence. It has nothing to do with they being equal, unequal. This has been derived from a mathematical expression for PT. If you look at that, right? This block diagram has been derived from our understanding of what PT or P omega should be like, right? And therefore, if we interpret this picture properly,
mathematically show this that Ck is equal to AK minus 2, like you did in modified binary. Out there you had shown it is equal to AK plus AK minus 2.
this is modified duo-binary only we are talking about.
What I'm talking is like in duo binary, sir, you had shown that Ck is equal to AK plus AK minus 1 diagrammatically.
Yes,
It's
yes.
going double, that's what I want.
Okay, you want it to be related to this picture here, right? I think for that you have to just look at some delay. I have to introduce some delay. Okay, suppose I delay it by 2t0 seconds. Not 2, I think the delay should be t0. This is,
So it's 2
no, this
AK
2t0.
minus AK minus 2 has to be 2t, sir.
No, that is okay. In this block diagram it is 2t0, but with respect to the original expression, how much delay, when I factored it out, how much delay was being introduced? Was it t0 or?
2T0.
No, I am not sure. No, see, okay, I think you're, no, it's okay. What I am saying is like this. This is my original P prime omega for the duo binary, right? This is okay. And this is what I get after factoring things out. And how do I factor? I basically am taking e to the power j omega t naught out, right? E to the power j omega t naught. Okay, let's put it this way. This p double prime omega that I'm really going to get from this block diagram is this p dash omega into e to the power minus j omega t0. So with respect to the original p prime t, what you are getting here is a delayed version with a delay of t naught seconds, right? This 2t naught is coming from this realization.
Repeat the second last sentence, that the T naught we are getting is.
Okay, this p prime omega and p double prime omega are identical spectra, identical pulse shapes, except that this pulse shape is delayed with respect to t by an amount of t naught seconds.
So what we are plotting, modeling in that block diagram is P double dash of
Basically what you are modeling is p prime t minus t naught, right? So therefore at the kth instant the pulse that is coming to the picture is a delayed version of this pulse. Just like in the duo binary case, I had a delay of t naught by 2, here I have a delay of t naught. Now you interpret the waveform. So basically this minus t0 becomes your sampling instant, right? Isn't it? If you delay it by t0 seconds, your 0 will be shifted, I mean this peak will shift to 0, right? Therefore, when I am sampling here, I am also getting a contribution from one previously transmitted pulse, which was transmitted at
2t0
two intervals behind, and that its contribution will be this negative peak, right? If both are positive, right? Okay, I'll have to draw it for you. No problem. So I have shifted this here. This is one, okay, and the other one is okay, this one. This is the pulse that is being looked at for the kth bit, right? This was a pulse that comes to the picture for the k minus 2th bit. All right, same thing displaced two time intervals. This is one time interval, this is second time interval, right? So if you look at this sample value here, basically what you are going to get is this minus this, which is no, whether it is what I have drawn here is a situation where I have assumed ak and ak minus 2 to be both 1. So whether this will be 0 or something else will depend on what is the sequence of bits that comes into play. Okay, for example, if ak minus 2 was negative, this whole pulse shape will be inverted and you will get a superimposition of the two. But the important point is this relationship, which is what you had doubt about. Okay, is that doubt resolved now? You wanted that physical picture, I hope it is there now with you. Okay, fine. So should we return to these two relationships now? You are all clear that for the duo binary case the sample values are given by this, and for the modified duo binary case the sample values are given by this. And we have already seen that these relations enable us to correctly interpret the data from X case regarding A case, right? We can make correct interpretation of A case if we just observe X case, right? But there is a possibility of error propagation, which you would like to avoid through pre-coding, right? So, and I think we had certain amount of problem yesterday with pre-coding, so we'll go over it again. You want me to do pre-coding for both the cases, or if you do for one, I think you can work it out for the others. We'll do for the modified duo binary, and you can, if you still have some doubts about duo binary, I'm sure you'll be able to resolve them yourself. If not, we can always talk about it again. Let's take the pre-coding for modified duo binary. I think that is the one which was giving more trouble to us yesterday. And what we suggested was that we should transform our bit sequence AK to a new bit sequence BK such that BK is AK exclusive OR with BK minus 2, right, for the modified duo binary case. Okay, let's start from here. Okay, Then what happens to your CK? Actually, is this XK or this is, well, we can call it XK or something. It does,
So when you are drawing AK, BK, you just write what exactly each is coming. That makes it possible. Like AK is the original signal, BK is the precoded signal.
this is the original data. Sequence, and this is the encoded sequence or pre-coded sequence, right? Fine. Okay, I think I will avoid CK altogether and will just write XK uniformly. Fine. So XK now becomes, what we are now doing is taking these BKs as data coming into your dual binary, modified dual binary signaling scheme, right? So the impulse sequence that is coming in into this system is no longer AK delta T minus KT0, but sigma B sub K delta T minus KT0. That is what is being transmitted. So this XK, the samples here, would be related to these BKs through BK minus BK, B sub K minus B sub K minus 2. So XK is B sub K minus B sub K minus 2. Okay. Let's start from this neatly now. XK is B sub K minus B sub K minus 2, which we can write as BK, if you remember, is AK plus BK minus 2 minus BK minus 2. I think this is what we discussed yesterday also. I'm just repeating it. Now what we like to appreciate is whether or not we can decode the value of AK from an observation of XK, which is what we'll be able to observe without intersymbol interference, right? XKs are the ones which we'll be obtaining by sampling the received waveform at each of the sampling instants. Okay, all right. Let's talk about the situation when XK is 1. Let's talk about one thing at a time. When XK is 1, in what way we can get XK equal to 1? If and only if BK is 1 and BK minus 2 is 0, right? If BK is 1 and BK is AK plus BK minus 2 and BK minus 2 is 0, what will be AK? BK is 1, that means this is 1, out of which BK minus 2 is 0, so AK has to be 1. Is it clear with everybody? Vivek? Understand this? Good. When XK is minus 1, the only way we can have it is BK is 0 and BK minus 2 is 1, right? And the only way we can have that is if BK minus 2 is 1, the only way this BK can be 0 is when AK is 1 again, because 1 exclusive OR with 1 is, right? When XK is 0, of course I didn't argue out again for you that XK can take 3 possible values only, right? 0 and plus minus 1, because of the fact that XK is BK minus 2, right? If BK and BK minus 2 each take 0 and 1 values, then XK can take only 3 values, namely 0, 1 and minus 1, and we are considering all the 3 values here, alright? In this case, they have to be equal, right? That means BK has to be the same thing as BK minus 2, which means this expression must be equal to BK minus 2, which can only occur when AK is 0, right? Then whatever is the value of BK minus 2 will be the outcome of this exclusive OR. This simple thing is what we got confused with yesterday, very simple logic, there was no need to, and that is our decision logic. When XK is plus minus 1, conclude that AK is 1, when XK is 0, conclude that AK is 0. And now we can do this data decoding without reference to what was transmitted in the previous bit interval. right? By just looking at the current sample xk, we are able to make decision about the current value of the data ak.
Last case, please repeat the last case.
This xk equal to 0 implies bk equals bk minus 2. Only then it will be 0, right? Which means that this sum, this exclusive OR must be equal to bk minus 2. And when will this be equal to bk minus 2? One of the terms is bk minus 2. It has to be when ak is equal to 0, because then 0 exclusive OR with either 0 or 1 will give you correspondingly 0 or 1. Right? But if ak is 1, we cannot get that. We cannot get one exclusive OR with bk minus 2 is bk minus 2. Right? Only 0 exclusive OR with bk minus 2 is bk minus 2. Right? That's simple logic for you. Fine. So I hope that resolves the issue of decoding as far as the modified duobinary is concerned, and the duobinary is in fact a bit simpler if anything. So you should be able to work it out if you still have some doubts. Okay. Now, if all this is cleared up, there are a few comments I'd like to make. What we have discussed is two examples of partial response signaling. And if you look at these two examples a bit carefully, you will see a connection or you will see a relationship between both the examples, in the sense that they have a very similar philosophy of working. That is, we generate a composite pulse shape pt which is obtained by linear combinations of sync pulses, which are all band limited to the Nyquist band. Our primary purpose is to communicate with the minimum possible bandwidth with perturbation tolerant waveforms. So these two examples are examples of generating the so-called perturbation tolerant waveforms by linearly combining sync pulses. In the modified duobinary case, you took sync pulse at t0 and minus t0. In the duobinary case, you took at t0 plus t0 by 2 and minus t0 by 2 and things like that. One can obviously generate other pulse shapes which will have similar desirable features. In fact, we have seen that not only we can get perturbation tolerant kind of characteristics, like we have gone from duobinary to modified duobinary, we got something else too. We could introduce spectral nulls. So in other words, this gives us a mechanism for doing spectral shaping just the way we were doing things in line coding. In fact, if you think about these things a bit carefully, you will notice a close connection between what you were doing in line coding and what we are doing here. In line coding, we were suggesting methods for representing ones and zeros when a number of ones come together, a number of zeros come together, and things like that. Right? Excuse me.
So, just one question, sir. Like in modified scheme, we have achieved spectral null at 0. And what else? I mean, what is the other advantage? That is the basic advantage over duobinary.
Oh, duobinary, that's the only
That's
advantage.
the only advantage.
That's a very important advantage for us, right? But what I'm trying to say is that all these things are being brought about by introducing what you can call correlation between successively transmitted bits. Your original data AK is uncorrelated. We are assuming that the bits are occurring independently. But after being operated upon by these pulse shapes, by the introduction of this so-called control amount of intersymbol interference, the successive sample values are no longer uncorrelated. They become correlated because xk, for example, now depends not only on ak but also ak minus 2, right? Similarly, in the case of modified duobinary, it depends on duobinary it depends on ak and ak minus 1. So introducing a certain amount of correlation between what the samples that are finally getting transmitted, and this mechanism of introducing correlation again carries out a spectral shaping of the pulse, right? And by linearly combining sync pulses in other ways, you can generate other kinds of partial response signals, right? I'll just very briefly talk about, therefore, generalization of these concepts. And I'm generalizing it in the following manner. In the duobinary case, we said that two successive pulses will interfere with each other. Two successive bits will interfere with each other. In the modified duobinary case, these two interfering bits were separated by let's say over 3-bit intervals, right?
2 bits.
No, if you look at the span, it is k, k minus 1, k minus 2. 3 spans are coming to the picture. It so turned out that k minus 1 did not interfere. But if you look at the total span over which intersymbol interference is taking place, it is 3-bit intervals, right? And one can generalize it to any amount that you may want, right? So let us say we are talking about a generalized system of PRS in which a small, of course we won't like it to make it too large, finite number of samples or sample values are allowed to be non-zero. So in a way this is generalization of the Nyquist second criterion. Instead of only permitting 2 successive bits to be interfering or only 2 non-zero samples coming up in the sampling instance of the pulse shape, you are allowing a finite number of them to be non-zero. In the sync pulse, ideal Nyquist first criterion pulse, any Nyquist first criterion pulse, only one sample is allowed to be non-zero, right? And now we are allowing successively more and more pulses to be, more and more samples to be non-zero. And let's assume that this value is n. Let n be the smallest number of, let us say, or what we can call contiguous samples which span all the non-zero samples. Okay, so you understand what is n? N is a symbol denoting the span over which all these non-zero samples exist at regular spacing of t0 seconds. For example, in duobinary n is 2, in modified duobinary n is 3, right? And what we need to specify further is the sample values. In the 2 examples that we have just done, the sample values were, okay, what were the sample values in the case of duobinary? 1 and 1, or f0 and f0, right? In the case of modified duobinary, it was f0, 0 and minus f0, right? Over the 3-bit interval, 3 values or the non-zero span of 3-bit intervals, non-zero sample values were f0 or 1, 0 and minus 1, whatever you like to call it, right? So in general, let us say, let f sub k, k going from 0 to n minus 1, denote the corresponding sample values, denote the non-zero sample values.
F naught minus F naught and 0, isn't it?
No, 0 is not.
No, only F naught.
F naught and
0
minus
will
F
replace the transition. It will be the complex of the previous one, isn't it? Complement, sorry. Complement.
No, you
No,
are
that is
understand-
only F naught.
These FIs are, I'm referring to the sample values of the pulses which will come to the picture at the sampling instance. There's nothing to do with data sequence. Okay, maybe I'll have to clarify this a bit. This was a pulse shape being used in duobinary, and the sample values that are non-zero which are coming to the picture is this value and this value, right? I think you've forgotten about duobinary.
No, I mean, so I would have to name the sample value.
At the sampling instance, the values of the pulse which will come into the picture,
Only xk. Isn't it xk?
xk's or pk's or whatever you like to call them, and in the case of duobinary, the sample values are these and all these, right? The non-zero values are only these two, right? These are the 2 non-zero values that come into the picture. Similarly, I'll again show you the modified duo binary. If I can find it quickly. Oh, I seem to have put it somewhere. Maybe I think I can quickly draw it for you. Modified duo binary scheme is in which you have, right, the sample values that come to the picture is this, this and this, non-zero sample values. Okay, all others after that will go through zeros, right? Here, 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 later on it will be all zeros. Yeah, so I'm talking about these three. Although it is 0, since it lies within the span of non-zero values, I'm counting it as, I'm denoting it by f some value, right? Some notation. Yes.
No, not on this. Yeah, on this only, the red graph.
Yes.
The duo binary pulse shaping. The peak values of f0 by 2, I mean the two separate sync functions, won't they occur at minus t0 by 2 and plus t0 by 2? You've shown them at minus t0 and plus t0.
No, I've shown them at minus t0 by 2. This is t0, this is in the middle, right? Maybe the picture is getting a bit small there, right? This is minus t0 and this is at minus t0 by 2. Okay? No problem. So, this f sub k is a notation for the non-zero sample values that are coming to the picture in the span over which non-zero sample values lie. Fine? Now suppose I want a thing like this. Based on your appreciation of what we have discussed so far, can you suggest a scheme for generating such a signal? A signal which has these properties, that is, intersample interference from n contiguous samples, right? Generate a pulse shape which will have, and the corresponding amount of intersample interference is dictated by these amplitudes.
Series of sync pulses.
A weighted sum of sync pulses with these as coefficients, right? Basically that's what you need to do. And you can realize this by a system of this kind. Based on what we discussed for the modified duo binary case, I'm doing this a bit quickly because there's really no new concept here. So I'm just going over it rather quickly, and I'm sure you'll be able to appreciate it without any difficulty. Oh, I think I should call it P omega.
So this was the question in the minor.
Precisely.
Summation.
So, which question was this?
That's a good one. I think it will be a good exercise to find that out. Alright, it was not exactly this question in this form.
Just to find out the summation of sync and whether it can represent, that's all.
That's right.
I mean displacement. the
It was
idea-
an example
that's
of a general partial
form of
responsibility.
representation.
So, if you generate it like this, where P omega is your, what will be P omega? What will be P omega? Ideal low pass filter.
Correct?
Actually speaking, a rectangular filter, right, of bandwidth f0 by 2. This f0 and f1 might confuse with that f0.
So what is the last
this is your pulse shaping filter. You see, here you are getting your impulse train, AK delta T minus KT0. See, the mechanism now becomes clear. What you are doing is, this is a very good way of visualizing how this controlled amount of intersymbol interference is really being introduced. You are doing it almost deliberately here, you can see that. This incoming impulse sequence carrying the data is allowed to interfere with each other through this delay line.
So now decoding will be very complicated.
More complicated, but possible. Because you know precisely what these FIs are, it's possible to do it. Right? You can set up a set of equations which will allow you to do the decoding. Right? But before we come to that, what I would like you to appreciate is that one can generalize partial response signaling in this way, which clearly shows that your pulse shape comes out as a result of two operations. One is introduction of correlation or introduction of intersymbol interference, and finally by passing it through a low pass filter, pulse shaping filter. Right? You could replace P omega with any G omega which satisfies a Nyquist criterion. It need not be your rectangular filter, incidentally. Right? You could replace it with any other filter which satisfies the Nyquist first criterion. You would continue to have the same advantage or same kind of property. But the only problem with that system would be that you will use up bandwidth more than the minimum Nyquist bandwidth if you use some other G omega which is not the rectangular low pass filter.
So what is the advantage of having so much of correlation when we have already achieved the spectral null with modified dual?
Okay, I'm presuming that as far as, I'll just come to your question, but as far as this concept is concerned, this concept of generalizing it is okay, right? There is no really any question on it directly. There are two questions that have been asked. One is regarding the complexity of decoding, and the second thing is why should we do a thing like this? What possible gains we might get? Okay, let me talk about both of these very briefly. As far as decoding is concerned, yes, certainly it becomes more complex, more involved. The corresponding pre-coding, if you have to do it, in fact most of the time you will do pre-coding because there will be error propagation involved otherwise. Right? Even pre-coding becomes more involved, but it is not that involved that one should not think about it. Okay, it's manageable, and I would like you to work out the equations for decoding as well as for pre-coding of general PRS systems. All right. Excuse me. So I'm leaving that as an exercise. I'm not precisely answering that question because that will take me quite a bit of time, and I want to now leave this topic and go into something else quickly. But because there is otherwise so much on each topic that when one can do a whole course on each topic, which we don't want to do. All right. The other thing is why do it? Now basically what we have learned from the experience with dual binary and dual binary is that we get a certain amount of flexibility to do our pulse shaping, right, by doing things this way. So depending on a specific application or a specific requirement, suppose in a particular application somebody says that I want to send a pilot tone along with a signal corresponding to the Nyquist frequency so that I can recover my clock easily. Right? Suppose somebody says that my communication system will work well in a particular situation provided I send a pilot tone of a frequency corresponding to the Nyquist frequency, which will correspond to the clock rate, or bit rate, half bit rate. Right? Now if you want to do that, you want to introduce a sinusoid component at f0 by 2, I must make sure that at f0 by 2 I have a null. Right? Fortunately both dual binary and modified dual binary have that also. Right? So I can easily introduce a pilot tone there. But similarly I may come up with some other requirement of putting a spectral null at some other place. So I could think of investigating whether I could create that kind of a property in the spectrum by using a certain set of weights in the partial response setup. Right? So basically what we are getting out of this is flexibility in design, right? Which can enable us, this flexibility will enable us to do a number of things. Flexibility to place nulls in the spectrum, make the system less sensitive to timing errors, but in any case the most important and overriding requirement is to design PRS systems which use practical or practically realizable or perturbation tolerant pulse shapes. Practical pulse shapes with minimum bandwidth. Right? That's the most important requirement. All other requirements are, perhaps you can think of them as side benefits. The main thing is this, that you are getting practical perturbation tolerant waveforms within the Nyquist bandwidth. That's the overriding requirement. Okay. So I think with that brief mention of general PR systems, I will close the discussion here. But I'll, for those of you who are interested to know more about it, I can give you one reference. Of course, there are many books now which deal with this, but there is a very interesting paper by Pasupati. I'm forgetting the initials. It is in IEEE Transactions on Communications. And I'm working with my memory, and I think I'm not able to remember immediately the year, but you'll find the reference given in your book by Lathe. If you look at the list of references at the end of this chapter, you'll find the reference there. It's a beautiful reference to read from for more about partial response signaling, if you want to know more. Okay? Okay. Now, where do we stand now? From our discussion of line coring and Nyquist criteria, you might feel that we have taken care of all problems of baseband communication. Of course, so far we have been talking about baseband communication, right? Baseband in the sense that we are not introduced the concept of a carrier. Okay? We are basically working with the pulse shapes to represent ones and zeros, and they were transmitting them after shaping them appropriately, right? Either shaping them or doing, before shaping, even doing some line coding and things like that. And specifically, we have spent quite some time on how to take care of intersymbol interference that is otherwise likely to be there on a band limited channel, right? And you might get the impression that that is very good. Intersymbol interference is taken care of. But life is not that simple in communications. Can you see what problems might practically arise in spite of all these designs that we discussed, Nyquist designs?
We have to know the channel characteristics.
Very important point. This what we have discussed so far is an overall framework within which we work, we will get nice properties. The question is, can we create that framework so easily, right? That is, can we really design the overall system without worrying about what the channel is like? We have to worry about, of course, that we appreciate that we have to worry about that, but we can worry about it, or we can take that into account, provided what we know the channel impulse response. We know the channel transfer function. If I know the channel transfer function, then I can ask a general question. Okay, here is the overall pulse shape requirement for intersymbol interference elimination. here is the channel transfer function. Now how should I realize the overall transfer function partly at the transmitter, partly at the receiver for this given channel so as to maximize performance, right? One can ask that question, and fortunately that kind of a question can be theoretically answered, but one has to formulate that question and formulate the answer to that question. Before I will take up that question separately, but even that question makes sense or can be useful provided you know your channel transfer function, right? There are many situations in real life communications where that is impossible to know. Even in a telephone line system, when you pick up your telephone either to transmit voice or data, you don't know precisely what is the line that is coming to the picture, right? How long it is, what its transfer function is going to be. It's going to be different even if same two persons talk to each other at different times, because you may go through a different route, right, to the same person. So the assumption that channel transfer function may be known so as to take that into account is also not a very valid assumption in all situations. In some situations it may be possible, but in all situations it may not be possible. Therefore, it seems almost impossible that we will be able to take care of intersymbol interference just by doing paper design once for all, right? We will necessarily have intersymbol interference, and that fact of life we will have to face at the receiver. When you are trying to receive the data, we will have to live with that intersymbol interference, and if we are clever, we will try to eliminate it at the receiver, right? And that is done through a process called equalization. That is, whatever you do not know about the channel, you try to learn about it from what you receive and then try to compensate for it. And that process is called adaptive equalization.
So, what is adaptive equalization?
So we have introduced two new terms here. One is equalization, which takes care of the fact that it can compensate for departures of the channel transfer function from what you might have assumed, provided you know what those departures may be. If you don't know what they are, then you have to take recourse to first learning about these departures and then taking care of them, and that process is adaptive equalization. So you estimate your channel and then use the channel estimate to compensate for its characteristics, right? These issues, it will make more sense if we take them up slightly later in our course. So I will return to intersymbol interference again later in the course if we have time, okay, and discuss these issues a little bit further. Yes, please.
P omega, which we just considered just now and modified all these schemes, that is essentially P, the original pulse shape, pass through this channel function, because we had said PT equivalent is equal to
P omega is, let us call that, let's call it PT omega, PC omega and PR omega, right?
Yeah, so
If I know PC omega, I can design an appropriate pair of PT and PR such that we get overall PR omega as follows.
Overall P omega is what we have considered.
We know what overall P omega should be. So if PC omega is known, life is okay. We can work with it somehow. The problem is, what if it is not known, right? That's where equalization and adaptive equalization makes sense.
So earlier you said that we can't use time sync wave because of the time jittering problem. And here also, won't those problems arise because we are again happening at a particular instant of time.
Yes.
So when there is a small incoherence in the time, so won't there be any problems?
No, I think I understand your confusion. It's a very important question that he has asked, which shows that some of you may still have some lingering confusion regarding partial response signaling. The confusion may come from the following fact. What we have done is we have generated a partial response pulse shape through linear combination of sync pulses. and that is where your confusion is coming from, right? But what we are really doing by this linear combination is generating a new pulse shape. That new pulse shape has the features that the corresponding spectrum is no longer a sharp transition spectrum, a brick wall kind of spectrum. It is a tapered kind of spectrum. The fact that it has a tapered kind of spectrum implies that the corresponding pulse shape has small side lobes which also decay very rapidly in time, right? So although the composite pulse shape that we have used for construction of our new pulse shape happen to be sync pulses, the resulting pulse shape has nice properties.
Then you want to say that even if there's some time jittering, f naught will be slightly plus minus delta f. The value of
The effect will be only marginal.
It will not be
Right?
much.
That's the whole idea of perturbation tolerance, that we want to be able to tolerate to perturbations in timing, which we will be able to do provided our side lobes are small and they decay very fast with time, right? So that was a very important and valid question if this fact was not understood very clearly, that although sync pulses are being used as basis functions, the final pulse shape is no longer a sync function, it is something else, right? Okay, I think this is a good point to stop. We will talk about digital modulation techniques from next time onwards. Thank you very much.